What's up, everybody? Now we are going to take a look at this very important problem. We are going to find a or compute the Lyapunov function or to prove global asymptotic stability for a given autonomous nonlinear dynamical system. Okay, and all right, for a given dynamical system, this is our dynamical system. All right, we need to find, and of course, before you do any of this, you would use ODE45 and simulate starting from a bunch of random initial conditions, right, starting points, and you would look at the trajectories, and if you consistently see all the trajectories, right, and of course we are talking about global stability and anywhere in the state space, and if all those trajectories go to converge to origin, you would be at least confident, right, that this system would be asymptotical stability, would have asymptotical stability. And to prove global asymptotical stability, and of course there are other variations like global exponential stability, right, but this is like the first case, right, and we are going to look at this. And to prove that, you need to construct a Lyapunov function v of x, okay, and 1, 2, 3, 4, and there will be 4 constraints that you need to impose on this function. And since we are talking about global stability, you can also, I should have also written something like this, but do I have space? Maybe I should do something like this. Okay, v of x goes to infinity as norm of x goes to infinity. Yeah, this will be the 5th constraint. Okay, and in the previous video, like I just published like 1 hour ago or something, and we have talked about SOS polynomials and SOS programming, right, and how useful they are, and they are also useful for us to construct the Lyapunov function. Okay, and now we are going to look at this problem again, and let's go to MATLAB. Let me just first click on that. Okay, first of all, just add, it says add MOSEC and YOLMIP, MOSEC or STP-T3, right, any STP solver for that matter. Okay, this is the first step. Okay, and by the way, don't get scared by that, just look at this, and it is almost like, yeah, it's 20 lines of code, and it's very simple. All right, first of all, clear and tick and talk for just to measure the time elapsed, right, and we will look at the 3-dimensional dynamical system. Okay, and f1, f2, and f3 expresses the x1, x2, x3 dynamics. Okay, and these 3 equations, dynamical equations, basically express how the trajectories evolve in state space. Okay, and this term basically says we are going to use that variable to indicate that we think our Lyapunov function, the degrees of it will be 4, right? If you, and it is an in a way iterative process. If you are not able to find one, you would increase the degree and search for a Lyapunov function, right, among the 6 degrees, or among the polynomials whose degrees are 6 and less, right? Okay, all right, and yeah, this is okay. Maybe I should go back to the board. Okay, this is the problem, right? And how we are going to change this problem? We are going to manipulate, right, this problem, and we will put this in a SOS programming framework. Okay, moving on. First of all, this is our original problem, right? V of x here, v of x being positive, we will change that by this expression. Okay, whenever you see positive, we will in a way almost always change that with some type of SOS constraint. Okay, all right, and here epsilon 1 and epsilon 2 here, they are like, maybe I should write this, epsilon 1 is 0.001 or something, right? Very small number, right? Okay, and first of all, again, first we will define a Lyapunov function, or v, a polynomial, right? And we will sum for each polynomial, there is some corresponding monomial vector and coefficient vector. Okay, basically we will try to find those coefficients. Okay, let's go back to MATLAB again. Let's keep this constraints in mind. Okay, so that term basically, yeah, wait a sec, just keep that highlighted term, epsilon times x norm square. Okay, and all right, the term that we call eps1 polynomial is this basically. Okay, all right, so all right, let's move on. Okay, here first initialize v, polynomial v, and for each, I guess, decision polynomial, right, we have corresponding coefficient vector, right, and monomial vector. Okay, and again we need to compute v dot, but I prefer to rather than saying v dot being negative, right, I like to say minus v dot and m v dot, right, minus v dot being positive. I like to say that. It's convention, I guess, my convention. And here we are just defining our STP solver. Okay, and here constraints again, v being positive, minus v dot being positive, and they reach 0 at the origin, and again the same constraint for v dot. Okay, here we are going to stack our constraints on top of each other, and then we will supply our constraint set, and by using those constraints, the optimization tool will compute for the coefficients. Okay, here these are the coefficients that we need to compute. Okay, let's check the first constraint. Yeah, this basically indicates that, right? I'm sorry, not this. Yeah, this line basically indicates this constraint, right? Imposes that constraint. Okay, that's great. And here again, this line basically expresses that constraint. Okay, great. And yeah, this, we haven't talked about this, but since in a way we have a lot of degrees of freedom, right? And just to limit the degrees of freedom, in a way you can think of it that way, and we impose that constraint as well, right? because if you have some v Lyapunov function, basically you can just multiply it with any positive constant, right? Any positive number, right? And that Lyapunov function will still be a valid Lyapunov function for your, dynamical system. So any Lyapunov function that is valid that you computed, right? By just multiplying with a scalar, we can make that Lyapunov function in that form, right? Satisfy that constraint. Okay, that's great. And again, this all the coefficients being, being greater than 0 and equal to 0, or being in the interval of 0 and 100, right? This is just to limit the degrees of freedom. Okay, all right, some type of numerical, I guess, reasons we are doing this. Okay, and yeah, okay, just keep that line in mind. Okay, let's go back to board. Yeah, basically this, right? Identical. That line is identical to this red circled expression. Let's go back to MATLAB. Yeah, v minus epsilon polynomial, right? And epsilon polynomial is like this expression, and that term must be SOS. Okay, and also the same. Let's get back to the board. Okay, and here the same constraint, right? Again, we are imposing that constraint. Okay, and this is the syntax of source command of YOLMIP. Okay, and here constraints f is the object that we put our constraints in, right? And since this is a feasibility problem, we don't have any objective to minimize. Okay, using changing, tuning our decision variables. All right, and options. In options, we define that, hey, we have MOSEC and we want to use MOSEC as our STP solver. All right, and what are the decision variables? For example, x1 and x2 and x3 for that matter, they are not decision variables. They are indeterminates, right? And it's like, yeah, it is like a term that's been used in SOS programming. Okay, and we will try to find these decision variables. What are the decision variables that we need to find? Coefficients of the Lyapunov function, of our Lyapunov function. Okay, so, and tick and talk for just to measure the time elapsed. Okay, press run it, and it's amazing, right? It's like 2 seconds. Okay, and it says successful solved. All right, that's great. And just 20 lines of code would get you a Lyapunov function. That's great. But if you are a little bit of a skeptical person, right, and you check that again, if the Lyapunov function that you computed is positive and also v dot is negative, right? Just you can use that. It is complete the MATLAB, I guess, coding, right? And just run this code, run this section. Okay, because we have coefficients. Okay, and we also have, anyway, I mean, you can look at this. It's like, if you look at the codes line by line, and for example, this is not the same replace as this one, right? This is YOLMIP command, but this is MATLAB command. Okay, MATLAB string command or char vector. Okay, but it is not important. I think you don't need to know that, right? And just run this, and what you will get is your Lyapunov function. And of course, it's an incredibly long expression. Okay, but yeah, and then as a symbolic object, you can run this section again. don't think about that hard, okay? And you can of course manipulate this script to work for 2-dimensional, 4-dimensional, etc. systems. You just need to be aware of those, dimension of the problem, defining the dynamics, etc. That type of, administrative stuff, or bookkeeping stuff, I guess. Okay, so this is our view upon a function, right? And now we need to determine if this view upon a function positive indeed SOS, right? Indeed positive definite. Okay, let's run it, and it says successful solved. Again, I have talked about this code, right? Or at least the logic of it. What we are doing is this is a problem of determining if a given polynomial is SOS, right? Because we reduce the problem of being positive to some type of sufficient condition, which is that polynomial being SOS. Okay, all right, that's great. And we are just using that. In the previous video, I hope I can add the link to that video. We have talked about this code in detail, right? What is the problem? Given a polynomial, determine if that is an SOS, sum of squares polynomial, or positive polynomial. Okay, all right. But again, polynomial being positive and sum of squares, it is not if and only if condition. This SOS implies positiveness of a polynomial, but not the other way around. Okay, and we are just using some sufficient condition, but that by using that sufficient condition, our problem becomes really easy, right? Okay, all right. Because I mean, there are some things called Motzkin polynomials or something. They are positive, but you cannot find express them as SOS, right? They are just some type of anomaly, I guess. Okay, and all right. So it says we run this section, right? Wait a minute. Yeah, we run this. So it says successful solved, meaning our view upon a function can be expressed as SOS, meaning it is positive. V of x is positive. Okay, that's the takeaway. All right, and this section tests, right, checks if our view upon a function, if the corresponding v dot is negative, okay, or rather minus v dot, corresponding minus v dot is an SOS. Okay, run this section, and again it says successfully solved, meaning we were able to find a SOS polynomial, or we were able to express that polynomial as a sum of squares, meaning minus v dot, okay, minus v dot, because here we are just computing first of all minus v dot, and then finding, I mean, I could have written like, wait a sec, yeah, there's something wrong with that. Yeah, wait a sec. Okay, I hope that works. Okay, got it. Okay, because yeah, okay, all right. I think you just realized what was the error. Okay, I just copied and pasted. Yeah, be careful when you copy and paste, right? Okay, and yeah, finally, again, in that section we determined that minus v dot is positive. Okay, that's great. And let's write v, and let's display v and v dot terms. Okay, Yeah, let's run it again. Okay, of course, again, I mean, it is extremely long expression, okay? And you don't need to, I guess, what Lyapunov function is really not important. Is not that important. What is important is you are able to find one, okay? And if you are able to find one, you are done with proving the global asymptotical stability. Okay, by the way, before, yeah, you can again download this source Lyapunov 001.m, okay? This is the script, okay? You can download this from the GitHub page, link given in the description, okay? And here, this, like, I guess, like 20 or something, right? 25 lines of code. This is for, yeah, maybe make it larger. This is for, yeah, we are just running bunch of OD45 simulation, okay? And as you can see, all the trajectories, let me just run it again, right? All the trajectories converge to the origin, okay? And this section is the first thing that you will do, right? By the way, you will do that, and if you see, okay, all the trajectories go to origin, converge origin, meaning, what does it mean? It means that you have some credible suspicion that the system might be global asymptotical stability. Okay, asymptotically stable. All right, and then you will go and try to find the Lyapunov function, compute a Lyapunov function to prove that it is in fact your suspicion is correct. Okay, that's all. Wait, is that all? Yeah, this is, I will name this video global asymptotical stability, right? And I will publish another video, and in that video, for example, we just look at the global case, okay? However, I mean, there are local cases and they might occur a lot, right? And in the next video, we will look at local version of it, right? We will not construct the Lyapunov function where the constraints are satisfied in all the points in state space, okay? But only in the small neighborhood, or the neighborhood of that, some specific neighborhood of the origin, okay? All right, that's, again, you can download this video. I guess you can download this video. You can download the script. It's called source Lyapunov 001 from the GitHub. Okay, thanks for watching.